I'm just going to give a small introduction.
Okay.
You can start. Great. Hello and welcome everyone to the International Physics Symposium. I am very pleased to introduce you today to a very inspiring and respected figure in the physics community. As a theoretical particle physicist, Dr. Quinn did groundbreaking work during the 1970s in a long-term quest for a unified theory of the fundamental interactions in particle physics. The relevance of her work granted her the honors of receiving the Dirac Medal from the International Center for Theoretical Physics, the Klein Medal from the Swedish National Academy of Sciences, the Saccharoid Prize from the American Physical Society, and the Compton Medal from the American Institute of Physics, among many others. In addition, Dr. Quinn has also been very active in science education. Some of her work includes serving as a chair of the U.S. National Academy of Sciences, Board on Science Education, being a founding member of the Contemporary Physics Education Project, working as a member of Comisión Gestora at the request of the President of Ecuador, and involvement in many other projects which have had an international impact. Dr. Quinn also holds the position of Professor Emerita at Stanford University, where she obtained her PhD in 1967. Thank you.
Thank you very much, David. And as you can see by my title, this talk is historical as much as it's a physics talk. It's about how physics works and how physicists work, and about how mathematics and physics play together. So for those of you who are not physicists or physics students, it's learning to think about the things that aren't in the textbooks. When we tell you about well-established physics theories, we tell you what the theory is, not the struggle we had to get there. And it all seems as if people brilliantly came up with this theory clean and complete, but it never works that way. We stumble through ideas until we get to one that works. And this is the story about a particular idea, work I did with Roberto Peccei. Unfortunately, Roberto died last June. So how can I advance my slides? That is my question. It's not moving. My slide is not moving, so I have to play with that to get it to work. Let me see what I can do. Page up, page down. Oh, there we go. All right, so this is a picture taken in the mountains near Aspen, where there's a nice place where physicists go and work for the summer. I'm the one in the back in the poncho holding the plastic water bottle, and Roberto is on the right. The other two are Bill Bardeen and his wife Marge, who also plays a role in the story we're talking about today. But Roberto was a wonderful man. He was a great physicist, but also a great administrator, teacher, mentor, advisor to many. He was also a man of the world. He was born in Italy, grew up in Argentina, came to MIT as a graduate student, and stayed in the US and then in Germany and then back to the US. So he lived all over the world, and wherever he went, he worked with lots of other people and was generous, kind, thoughtful, and wonderful to be with. So this is just a moment to think of the joy we have in working with others. The plan of my talk is this is a talk where I start with some background, and there's a lot of background you need to understand the particular technical piece of work that Roberto and I did together, which now goes by the name of Peccei-Quinn Symmetry. And then a little bit about the work and some of its consequences. So how do we use mathematics in physics? We start, of course, from observations. From our observations, we build models and theories. And in physics, if we write those theories as mathematical equations that describe the relationships between the physical entities. A good physical theory correctly summarizes a significant number of observations, and it predicts new possibilities of things that might be quite unexpected before you wrote the equations. but they can be tested. And so if a good theory is one that has survived many such tests. One example is Maxwell's equations, the equations of electricity and magnetism. Maxwell's equations introduced the fields and their relationships and predicted electromagnetic waves. Hertz was more the experimentalist. He was testing, and he designed and produced both radio antennas and receivers in order to detect the waves that were predicted by Maxwell's equations. I love this quote from Hertz. It says, "One cannot escape the feeling that these mathematical formulae have an independent existence, an intelligence of their own, that they are wiser than we are, wiser even than their discoverers, that we get more out of them than was originally put into them." And that's the nature of a good theory. He was talking about Maxwell's equations, but in fact, when Dirac wrote Dirac's equation, he predicted antimatter. Nobody would have thought of antimatter, but the equation said it had to be there. And then we went and looked for it and indeed discovered it. Took a while to figure that out. Sometimes the equations are a little opaque as to what they're predicting. The next piece of mathematics is symmetry. Now, in geometry, we all know what a symmetry is, and we know them when we see them. They're invariances in the equation for shape that give us beautiful appearance that has invariance under a rotation, for example, for the vases here, or under at least five-fold symmetry for the flower. If you write equations to describe these shapes, these equations do not change when you change the axes. If you move the axes from being the middle of one petal to being the middle of the next petal, you will get the same set of equations. So an invariance in the physical shape reflects itself in an invariance in the equations that describe those shapes. Physicists take that idea and use the term symmetry for any invariance of the equation. So when physicists say symmetry, they mean the equations describing this system have an invariance under some changes of coordinates. For example, physics doesn't depend on where you are or if you're moving at a constant speed. Once you say that, you know that the equations must be written in such a way that they don't depend on the choice of origin or the direction of axes, or indeed the frame of reference. So if the equations have that symmetry, then physics doesn't depend on where you are. But there's an amazing thing that comes out of that. The consequences of those symmetries in the equations are conservation laws in the physics. Energy, momentum, and angular momentum are all conserved because of that symmetry in the equation. So when we say energy is conserved, it is not an observational fact. It is a consequence of the observational fact that physics doesn't depend on where you are or which direction you're looking, or whether you're moving at a constant speed or sitting still. So this is something very surprising and very consequential, because symmetries also simplify the world. They make powerful predictions. And because there's conservation laws, that means certain things cannot happen, right? If you don't have enough energy, you cannot do certain things. There are forbidden processes coming as a consequence of conservation laws. And I find when I talk to non-scientists, the fact that we can definitively say that something cannot happen is perhaps more surprising to them than the fact that we can predict what will happen under certain conditions. So the forbiddenness of processes really simplifies what you have to think about, right? If you don't have enough energy, then all the processes that require higher energy are not relevant to the system you're looking at. They're not going to happen. So these laws, they're simplifications of the equations in that they're invariants in the equation, but they're also simplifications in our understanding of the world. And it turns out in quantum physics, another consequence of symmetries is the states can be classified into groups that behave in certain ways under the symmetry. And these are absolute laws. If the symmetry is there, the law is there. If you see the symmetry broken, well, you have to change the invariance of the equation. You've got to rewrite your equations without the invariance. There's another very strange thing in many physics theories, and it's called spontaneously broken symmetry. In the physical example I give you here, it's not so complicated. You see the pen standing up on the table, and there is an invariance under for the pen under rotations about the axis through the center of the pen. Whichever way you turn it, it looks the same. So there's an invariance in this system that you would put into the equations. However, the ground state of this system is the pen lying flat on the table. And the pen can't fall down without falling in some particular direction. And there's no longer the rotational symmetry of the system. However, there are an infinite number of ways the pen could fall in any direction on the table. So there's an infinite set of equal energy, lowest energy states, an infinite set of ground states for the system. And that means there's a degree of freedom, which is rotating the pen on the table, where the lowest energy rotation is asymptotically zero energy as you go to zero angular frequency. So you have what in particle physics becomes a massless degree of freedom, which is called the Goldstone boson. So spontaneously broken symmetries also have consequences in terms of the kinds of degrees of freedom in the theory. So I'm talking about symmetries in the equations. What equations? In particle physics, the equations we're talking about are always the Lagrangian, which is a definition of how the energy depends on the fields. So it's the kinetic energy minus the potential energy. The Hamiltonian also is another way of expressing it, which is the kinetic energy plus the potential energy. The consequences of these equations are the equations of motion and the interactions in the theory. And the particles in these theories are the quantum excitations of the fields. So we write a theory which is a functional of fields, and it has terms which express the kinetic energy, it has terms which express the masses of the particles, and it has terms which express the interactions of the particles, where two or more different fields have a product term in the potential energy. And the coefficients of those products we call coupling constants because they scale the strength of the interactions. In field theory, particle field theories, there are three important discrete symmetries that are almost automatic. And in fact, when people first started writing these theories, they thought they were totally automatic. In fact, what's automatic is the product of the three of them. So let's talk about each of them. Once we have antiparticles, we have theories that involve particles and antiparticles. And there's a symmetry in those theories under the conversion of particles to antiparticles, or a possible symmetry. So if you take every particle and turn it into its antiparticle, and every antiparticle and turn it into the particle, so that's C. The second one is P, which is reflection, or actually it's reflection plus rotation. It reverses all the spatial coordinates. And then T, which reverses the roles of what's at the beginning and what's at the end. We start with some particles coming in, they collide, and some other particles come out. Under T, we take the ones that were coming out, turn them around and let them come in, and they go into the ones that were coming in, going out. So it's a reversal of the process in time. And until about 1956, people assumed that all field theories had all these symmetries because the simplest ones do. However, experiment told us otherwise. The product of these three is actually an automatic symmetry for any Lagrangian field theory if it has these particular properties, which are all desirable properties for a physical theory. Local means you have only products of fields at a single point. You don't have relationships between the fields at one point and the fields at another point directly. Hermitian, it's mathematically, physically, that means the energies of the eigenstates are real, which of course is something you would want. And Lorentz invariant, because we want special relativity, all those invariances I talked about earlier between position and special velocity built into the equations. Once you've got those invariances, you have CPT symmetry in field theories. And it turns out you also, if you have only a few types of particles, you also automatically have the product of C and P and T separately. So even when we discovered in 1956 that P is not a symmetry, that the weak interaction theory actually maximally violates P and C, but conserves CP, at least as seen in 1956, people still thought CP and T were both symmetries until 1964, when experiments said, no, it's not so. So to explain the not so, I have to explain some particle processes. What would be a process that violates CP? One would be that I have a process, say any X goes to some Y, and then the CP reflected process would be anti-X going to, well, spatially reflected anti-X going to spatially reflected anti-Y. Those under CP symmetry, those two processes would have the same rate. So if they have a different rate, that violates CP. Those such things have now been seen, but that wasn't how it was discovered. It's the next one that was discovered in 1964. The neutral mass eigenstates are not CP eigenstates. I will explain that to you in a moment. Or certain decays, a meson that has one CP cannot decay to a final state that has a different CP. CP can be odd or even. So there's two possible categories of states for neutral states. And finally, if the neutron were to be found to have an electric dipole moment, that would also violate CP, because you cannot, if you turn the neutron into the anti-neutron and look at P, you find that the dipole moment is a forbidden quantity under CP. So these are some of the effects you might see. The one we saw is the neutral flavored meson. So let's go through this. What do I mean by a neutral flavored meson? I mean a meson which is made out of an antiquark and a quark of different flavors. So the K meson is made out of an anti-strange quark and a D quark, or the anti-K meson is made out of an anti-D quark and a strange quark. And similarly, all these other ones, since we have 6 flavors of quarks we know about now, there's now a lot of neutral flavored mesons, but the K was the first one we came across because it's the lightest. Now, if I look at that, obviously under CP, a K goes into a K0. A K0 goes into a K0 bar, an anti-K. That means there's 2 CP states of definite CP, which I've written down below. They're the mixtures K0 plus K0 bar and K0 minus K0 bar. And one of those is even under CP and the other is odd under CP. And those would be the eigenstates if CP is a symmetry. And in fact, this explains something. What had seemed to be very peculiar is there are 2 neutral K mesons which are very close to one another in mass, but they have very different half-lives. And CP symmetry says, okay, only the CP even one can decay to 2 pions. whereas the lightest thing that the CP odd state can decay to is 3 pions. But 3 pions, if you just add up their masses, they're almost the mass of a kaon. So that's a very suppressed decay. There's not much energy released in that decay, and therefore it has a much longer half-life. And so the short-lived K was assumed to be the CP even state, and the long-lived K was the CP odd state. And the mystery of the 2 different kaon half-lives was explained by CP. Until in 1964, Fitch and Cronin checked this out. They did a clever experiment. They made a beam of kaons, and they waited till all the K shorts had essentially decayed away. And then they looked to see if they got any 2 pion decays. And lo and behold, they did. A very small fraction, but that told them the long-lived kaon had a little bit of the K even in it. So it's not a CP eigenstate. And that means the symmetry is not exact. But this was very difficult for the theorists because in 1964, nobody actually knew how to write any sensible looking theory that had CP violation. Because CP violation only happens when there are complex parameters in the theory and you get interference effects, which means that the process and the opposite process can have different rates. However, interference requires 2 different coupling constants contributing to the process with different phases. However, when you write a field theory, most of the coupling constants, and in theories with few particles, all of the coupling constants can be made real by redefinitions of phases of the fields, which are not measurable things. So in the end, you have to have more coupling constants than you have fields before you get CP violation. And that means you have to have lots of different types of particles. As you add, when you add one more field, you add as many more coupling constants as there are couplings between that field and other fields. So you have to have theories with lots of particle types. And in 1964, we didn't know lots of particle types. People would have laughed if you wrote a theory with as many particle types as we now have in the standard model. So theorists were very puzzled by CP violation. But modern theories can have CP violation, although, and it was 1973 when we really got to the point of having a theory that looks like the standard model, except it only had 2 generations of quarks. And Kobayashi and Masukawa won their Nobel Prize for writing a paper that said, oh, well, if we add 1 more generation of quarks, then we can make all of the coupling masses and coupling constants. We can no longer remove all the phases and we can get CP violation in the theory. Now again, in 1973, we only knew of 3 types of quarks. Not a lot of people were paying attention to the standard model because it required 4 types of quarks, and the 4th quark wasn't discovered till 74. So already 4 types of quarks was a stretch to most people. And here Kobayashi and Masukawa were saying, well, we either have to add an extra generation of quarks or we have to add more Higgs fields. Either way means more particles. And it didn't get a huge amount of attention at the time because there were many other problems people were working on about the standard model. But the 3-generation standard model really took shape. By 1975, the first particle of the 3rd generation, the tau lepton, had been discovered. And again, for a technical mathematical reason, once you have 1 particle of a generation, so we got 3 types of leptons, we needed 3 generations of quarks to get the full theory to work in the way the standard model was working, to have something technically called anomaly cancellation. I won't tell you what that is, but it's a mathematical requirement. So as soon as we found the tau lepton, theorists were thinking, okay, we need 3 full generations. So the theory that Kobayashi and Masukawa had described in 73 now becomes a popular theory in 75. And the theory also had a theory for the strong interactions, the QCD theory, which is the non-abelian SU3 of gauge interactions between quarks and gluons. But that added another problem, and this is the problem that Roberto and I were thinking about. We had been trying to understand these strange things called instantons, which are, again, a rather technical mathematical thing that appears in the QCD theory. They're not particles, they're events of a particular type. But those events introduce the possibility to violate CP in the strong interactions. However, I told you, nobody has seen a neutron electric dipole moment. And in fact, there's an upper limit on the neutron electric dipole moment, which is of the order of 10 to the minus 12 in natural units for a dipole moment. So that's rather small. And what that tells us is the CP violation of the strong interactions, which is expressed by this term that is parameterized with the parameter theta, is very small. It's less than 10 to the minus 10. Well, when you see a parameter that's that small, you'd like some explanation. It's a parameter that could take any, it's called an angle because it actually can take values 0 to 2 pi. And the argument that the limit from the neutron electron dipole moment puts a limit on theta brings us back to Bill Bardeen, who was in the picture at the beginning there. So the problem we were thinking about is, if QCD is the theory of the strong interactions, and if there's CP violation in the weak interactions, then how can it be that the strong interactions have such a small theta parameter? Because you cannot impose CP symmetry on part of a theory. If you have a theory that violates a symmetry, that symmetry is broken and that consequences leak into all parts of the theory. By higher order effects, the weak CP violation can infect the strong interactions and drive a CP violation in the strong interactions. So we know if it's there at all, it's very small. So the question Roberto and I were trying to answer is, why is this parameter so small? Roberto is the one who turned this into the right question. And as I say here, getting the right question is one of the biggest challenges in doing science. You always start with a very fuzzy question. And refining your question as you think about it is a very big part of refining, of getting to an answer, because you don't get to the answer until you're asking the right question. Roberto's answer was, can we write a theory where theta is automatically going to be driven to 0? It's going to come out that way no matter what happens. Is there any theory or symmetry or something we can add to the theory to make theta naturally 0? Well, first of all, we have to think a little bit about how one gets rid of this theta parameter. The physically effective theta is the one you wrote in the Lagrangian minus the phase of the quark mass matrix. Now, you might think a quark mass matrix is real, but it isn't automatically real. You can finish up with complex masses in any field theory, and then you make those masses real by redefining the phases of the quark fields by this chiral phase transformation I show you below. If you do that, it changes theta. So as you rotate the phases of the quark mass fields, you can change the value of theta and make all the masses real and put all that complexity into the phase of the QCD CP violating term. All right, that's fine. We've got real masses, but we've got non-zero theta. However, obviously, if we had any field where there's no mass, we can now chirally rotate away the phase of the massless quark and get rid of theta. So getting rid of theta is possible in a theory with massless quarks. Physically, however, we know that none of the quarks have zero mass. So that's not the answer, but it's a hint. And the other thing we knew, and here's the interesting thing where particle physics links with cosmology, in the early universe, it was hot enough that all the quarks were massless because the Higgs vacuum field had zero value. That means in the early universe, theta is an irrelevant parameter. You can tune it away. And this is where we got confused. So we were trying to think, okay, in the early universe, all these quarks are massless. So maybe I can just get rid of theta in the early universe and it doesn't matter. So that was our first mistake. We can set it to zero and that has no physical consequences. Wrong. But we thought it was so, and we started to try and write a paper explaining this wrong idea. And we went to talk to Steve Weinberg, who happened to be visiting at Stanford that year. And we didn't even tell him our idea. We just started talking about CP violation. And Steve stopped us and gave us a lecture on how CP violation works, reminding us that when you change the quark phase, do all those redefinitions of quark phases, you're changing the phases of the coupling constants, which are coupling constants between two different quark fields and the Higgs field. So if I change the phase of that field, I'm effectively changing the phase of the coupling constant. So as we were talking to Steve, immediately I saw that our idea was wrong. And I said to Roberto, I think we need to think some more about this. And we said, thank you, Steve. And we left. And we never told him what we were thinking. But, and this is also a general rule, when you start trying to think about things, you get wrong ideas, but your wrong ideas have clues to the right ideas. The mistake tells us exactly what we need to think about. When the quark masses do appear, they're proportional to the Yukawa couplings times the Higgs vacuum value. So in general, even though I've made theta equal to zero, when the quark masses appear, they'll be complex. And again, I have to make them real. And that brings me back to non-zero theta. But this tells us it's the Higgs potential we have to think about. How can we arrange the relationships between Higgs fields and quark fields so that it's automatic that as the universe cools and the quark masses appear because the Higgs field gets a vacuum value, it happens in just such a way that the quark mass matrix automatically has a minimum such that the phase of the quark mass matrix cancels any phase of theta. In other words, there's a symmetry in the theory until the quark masses appear, and that symmetry is spontaneously broken. You see my hat with the little ball. The ball can be anywhere around the rim, and it's the same. But if the potential depends, and it turns out it's the QCD, the quark field vacuum values, which give us an effect which breaks this symmetry and tilts the hat a little bit. So there's a minimum, but the minimum, because it comes from the QCD vacuum condensate, depends on the QCD theta. And therefore, the minimum happens when the quark mass matrix phase exactly cancels the theta phase, if this symmetry exists. Okay, to put this symmetry into the theory, we had to add Higgs fields. To achieve the symmetry, you can't do it with just one Higgs doublet. You need at least two Higgs doublets. We were really excited about this theory, and we knew we were adding new particles by adding more Higgs fields, but we didn't stop to investigate their physical consequences. Basically, we wanted to publish this idea because we thought it was such a good idea, and we weren't too sure that our toy model would survive investigation of phenomenology, so we didn't. But the point we missed is this is generic, right? Any theory like this has a very low energy mode, which is the oscillation of the ball about the low point in the hat, which is It's not quite a Goldstone boson because it's not quite a symmetry, but it's a very low mass particle. So Weinberg and Wilczek separately both immediately noticed that our published theory had a consequence. It predicted a very light, neutral, weakly coupled particle, which Wilczek named the axion. Actually, Weinberg called me when he thought about this, and he said, "Did you notice?" And I said, "No, you're absolutely right. That obviously has to be a particle, but no, we didn't notice." And so I was calling the particle the Higlet, but Wilczek published and he called it the axion. So that's what it's called. Actually, I don't think Fizerev would have accepted the name Higlet for a particle anyway. So in our theory, we just added one Higgs multiplet. Now, of course, once you predict a new particle, you have to ask, is it possible that this particle exists? And our version, our simplest theory, was very quickly ruled out. There were three different directions the constraints came from. First, direct searches for this light massless particle, weakly coupled particle. It couples to photons, so it's actually detectable. Secondly, astrophysical consequences. If you have a light and weakly coupled particle, it's a mechanism for transporting energy out of the center of a star. So the lifetimes of long-lived stars provide limits on the parameters of this light weakly coupled particle. And finally, cosmological consequences, because the vacuum values of these fields and the existence of the particles in the early universe are another source of mass in the universe. And if you put too much of them there, you can cause the universe to collapse by being too much energy density in the universe. So all of these things limit the range of possible theories. The currently viable theories look like ours, except they add more Higgs fields. And there are a variety of them, but all of them still have this light weakly coupled particle called the axion. Now, axions are a candidate for being the particle that makes up dark matter. This is a little strange because they're extremely light, much lighter than electrons. And that means if they were produced thermally in the early universe, as for example, neutrinos are, we know the distribution of density fluctuations in the early universe from the distribution of temperature fluctuations in the 2.7 Kelvin cosmic background radiation. Another long story, which I don't have time to tell you today. It's a beautiful story. And so those little density fluctuations in the early universe have to grow into all the structure that we observe in the universe today by gravity. But if you have very light particles in the density fluctuations, they're moving fast if they're moving thermally in the early universe, and their motion wins out over the gravitational attraction. So it's actually hard to make the dark matter out of very light particles. But because of the way the axions were formed as the fields got vacuum values as the universe came along, as the universe cooled, they're not a thermal population in the early universe. And so they're a possible candidate for being dark matter, even though they're very light. So they're a very strange dark matter candidate compared to other kinds of particles. And people are now actively searching for them in many places, and many experiments are being built now to do this search. Only a small part of the allowable range of the currently viable theories have been searched so far. None of them have been found, but there's lots of places to still search. Also, axions don't have to be dark matter particles. So people are also searching for axions which are not dark matter candidates, or axions produced at the center of the sun, for example, or axions which actually have no relationship to our QCD axions, except that they have this same property of being very light pseudoscalar particles. So the world of particle physics is now actively searching for these things. After many, many years of having only a few people searching, it's kind of exciting to see how many people are looking today. So here's what is, this is 2018 data. There's not much new. What you see is noise, right? You see nothing in the range, and you see that the noise is down at the level where the band between what the band labeled KSVZ, that's one paper which has one set of Higgs fields, and DFZSZ is another paper with another set of fields. And the noise says, okay, there's no particles in this range. If there was particles, we'd see a peak in this. So the little blue bar above says this particular mass range where we see this wiggle thing is excluded for axions. And it's axions in the range between 2.8 or something of microelectron volts. Right? These are the best limits today. There's a slight improvement over this, but you see there's a large range of masses where the theory, the band between the two theories, is still allowed. So over the next 10 years, these experiments plan to search the viable band, and either they will find axions or we will know that axions are not the dominant component of the dark matter. So to summarize, this symmetry is still the best answer to the question of why is there no CP violation in the strong interaction. So I claim it's a good idea. And getting there, we stumbled, but we got there. And that is the nature of how theories evolve. And it's still a good idea, even if dark matter is not made from axions. But it's fascinating to think that it's possible that an idea to explain a technical detail of the theory of the smallest things that exist might tell us something about one of the largest components of the universe that we don't know about, the connection between the very small and the very large that happens as you think about these theories, and in fact was an important part of the way we came to the idea of this symmetry, is an amazing fact about the world, because the early universe explores high energy physics in a way that no other environment could. So the connection between what we think about when we think about the very small and what we think about when we think about the very large is, to me, a fascinating part of all this story. And wouldn't it be fun, at least for me, if somebody discovers the axions and we find that we finally know what dark matter is made of. I kind of rushed through this, but that leaves us lots of time for questions.
Great, thank you, Doctor. We are now receiving some questions. I remind the audience that they can write them to the username preguntas for questions, and then I'm going to tell them. So we already have a few of them. The first is, what do you think about the work Frank Wilczek has done on the proposition of the axiom to solve the CP problem?
Well, I mean, obviously, Frank is an amazing physicist, right? He's done good work on lots of different topics, and he's been exploring not just this version of axion, but related ideas which take the same mathematics here and look at the consequences of this kind of thinking in very, very different contexts. And I find it fascinating, but all physics is speculative until it sees relationship with experiment. And that's another part of the message here, right? That this theory was formulated more than 40 years ago, but it's much, much harder. You can invent particles that are very, very hard to test, right? The theory has not been rolled out. That's nice, but it hasn't been discovered either, because it's really, really hard to do experiments to find things that have very, very little interaction with the things we see and measure. And these experiments are a form of creative genius and a form of persistence, which I deeply, deeply respect. It's much harder work than just making up a theory. You can make up lots of theories, but testing one of them can take 40 years. So.
Thank you. We're also asked, what do you think of him as a physicist, Frank Wilczek?
He's a fine physicist. What else can I say? No, he's great. He's very creative, and you know, he lives a little more towards the mathematical side than I do, but we've interacted many times over the years, and he's one of the people that's always interesting to talk physics with.
Thank you. We also have another question. What do you think about the story of the physicist Chien-Shiung Wu in the mid-1950s, related to the 1957 Nobel Prize in Physics, Li and Yang? What can this story teach us, speaking in the context of the historical relegation of women from the recognition process in science?
I think women is one of the issues, but I think the issue is also theory and experiment. I think theorists get far too much credit, right? Because the theory comes first very often, right? The theory comes up with a good theory predicts something, right? It not only explains what you already know, it predicts something. And so the prediction comes before the test. But as I just said, the test is a lot of work, and a lot of creative genius goes into deciding what experiment could actually test what feature of this theory and how to do it. And in this case of Wu, right, she was immediately when Li and Yang wrote the theory, people started testing. And there were actually 2 experiments published in the same issue of his Rev Letters, Wu's, and another one which was Lederman and, oh, I'm a bad historian, I don't remember the name of the co-authors of the other paper, but the Wu's was first and the other was second, but they were actually published in the same journal. So in giving Nobel Prizes, figuring out who gets the Nobel Prize for what discovery, the rule of 3, that you can't give the Nobel Prize to more than 3 people, limits the set. Now, you could have included Wu, but then what do you do about the second experiment that happened days after her experiment? So figuring out who gets the Nobel Prize, there's always people who could have been included who are not included. Whether she was not included because she was a woman, I think in this case, it's not really relevant. The fact that she was a woman doing those physics makes her an exceptional person, because there were very few women. I mean, even when I got my PhD, there were only 2% of the PhDs in the US were awarded to women at that time. And Wu is sort of a generation before me. And so she was unique in that she took on becoming an experimental physicist in a time when very, very few women did it. But I think in terms of Nobel Prizes and who should have got the Nobel Prize, it's arguable that it was because of the second experiment that she was not included.
Thank you, Doctor. It is true that sometimes we should give more credit to experimentalists. Now we have, what do you think about time crystals? Namely, these systems can break time translation symmetry. Do you think these kinds of systems will see important applications in the near future?
I don't exactly know what you mean by time crystals, so I have no idea. Time translation symmetry is, as far, I mean, look, physics is the same this year as it was 20 years ago, except that we know more things, right? And we have sensitivities to things. Looking out at the universe, we can test because when we look out at the universe, we look at processes that happened in the past, because the light from processes happening a long time ago is only arriving at us today. So by astronomical observations, we can test how constant the laws of physics are with time. And if the laws of physics are independent of time, then you have time translation symmetry. What we know puts very strong limits on how much change there is. We can never say there's none. All we can say is it's less than X. And there are no persistent observations that say any of the fundamental laws have been changing with time. So you must build your theory in consistency with that data too. And it's very hard to write a theory. I mean, the effect of any time translation invariance has to be consistent with observations of distant stars, etc. It's a game you can play, but it's really hard to write a theory that has a structure in time and is consistent with those observations, I would say.
Thank you, Dr.
Now, I want to also say, of course, the laws of physics don't change, but conditions change. Right? The conditions in the universe, in the early universe, are very, very different from the conditions in the universe today. So, of course, conditions change, and we have to investigate how the laws of physics behave under those different conditions. And eventually, when we get back to the very, very early universe, we get back to conditions where we have not observed the laws of physics. So we then are exploring new regimes. And that's one of the reasons putting together cosmology and particle physics tells us interesting things.
We're also being asked if you have participated in experiments for axioms of any kind.
No, I'm a pure theorist. I'm a klutz when it comes to being an experimentalist. I look at and talk to the people who are doing it and greatly admire their ingenuity and their, as I say, persistence to build an experiment that sees nothing and refine it and see nothing and keep doing it for 30 years is an incredible and getting better. I mean, until now, they are now, after 30 years of working on it, reaching the limit, the sensitivity that they wanted to get to be able to see axions if dark matter is made of axions. That's an incredible kind of persistence, as well as an incredible kind of ingenuity, because it takes good ideas to make these experiments better and better and better.
That's definitely true. It still looks like, though, that we're still very far away from proving such a statement, right?
Yes.
Someone is also saying that thank you, that the talk has been very inspiring, and is asking about the criteria for knowing how to know if the math we are using is right, beyond that it can successfully explain the observable phenomena and predict.
Well, first of all, of course, it has to be mathematically self-consistent, and mathematics has its own rules of consistency, right? So you have to be using a well-defined mathematics. You may be developing a new kind of mathematics. If you're writing string theories, you're adding ideas of mathematics as well as formalism for possibly describing physics. So that's one piece. Secondly, you have to, when you write a physics, you can write many mathematically viable physics theories that have nothing to do with the real world. The real world is only one of them. And so finding which theory describes observations, and then finding which observations haven't yet been looked at that this theory might predict, and untangling the consequences of the theory in a new regime and then testing it. That's the way physics grows, right? That's what physics does. The mathematics is much richer than the physical world in the sense of possibilities of theories you could write. But the physical world is the only thing that allows us to say this is physics, not just interesting mathematics. And that labels me as a phenomenologist. I enjoy the mathematics, but I am very much more interested in what does the real world tell us and how can we test this theory and rule out, if possible, the only way we make progress in physics is by ruling out theories. And we have to really work. What's happening is we build consistencies between theories that emerged in quite different domains. And I think this is where Einstein's genius came along. He put together things that were separate and said they're inconsistent. I have to fix it so that they work together consistently. And he did that for special relativity, and he did that for general relativity. In each case, he was taking things that were in various parts of the theory and seeing that they didn't fit together right, and then writing a new theory where they fit together right. The theories that existed before are special cases or limits of Einstein's theory. But the theory, the more general theory, is the one where all the pieces fit together in a single consistent description.
You think there could be more than just one mathematical framework that explains a single phenomenon?
Well, this particle physics is a weird thing, right? When I'm doing condensed matter physics, I can look at a lot of different phenomena which are really different conditions. And so I have to pull different pieces of theory for different conditions. But when you're trying to explain sort of what underlies all of it, there's one theory of particles, right? And if it's not consistent with all particle results. Now, in principle, our particle theory also explains condensed matter. In practice, we don't know how to do those calculations. We cannot take our one theory and predict all the properties of all the complex structures that we find in matter, or for that matter, in trees, right? The collective phenomena are much more complex and difficult to predict, and we can write specialized theories for certain types of collective conditions. Those theories have to be consistent with the underlying theory. So if the underlying theory says there's conservation of energy, those theories have to have conservation of energy as well. But they don't look directly. You have to explore deeply to see the relationship between the underlying theory and the theory that's explaining superconductivity, right? So there are multiple theories of physics because we're dealing with multiple ranges of conditions. But if we're looking for the fundamental particles that underlie everything, there's only one theory is right, and right meaning describing the world we live in. And we know the one we have today is an approximation to that, right? We know that there are conditions and things that our theory has not yet described to us, dark matter being one of them. So we know that the standard model, just the simplest form of the standard model, isn't the full story. But it's a remarkably good theory in that it gives us correct predictions for a huge range of experiments that have been done over 50, 70 years, right? From the time accelerators were invented till today. And any theory that goes beyond it will have to have the standard model as a limit case, as a piece of that theory that is an approximation to the more general theory under certain conditions, because that's clearly where we live. And
sure.
It's easy unfortunately, you know, and to some extent, I'm guilty because, you know, I wrote a paper with Georgi and Weinberg about how the strong, weak, and electric interactions unify to a unified theory of all interactions at some very high scale. We extrapolated because the coupling constants come together at a scale which is very far from any experiment we can do in the world today, or are likely to be able to do in the world of the future. So we always look at our theories beyond where we've tested them and say, oh, that's interesting. That's a mathematical feature that is a very interesting feature of the theory. But how we test that part of the theory that is at a scale which is totally inaccessible to our experimental tools is very, very hard. And so the space for speculation in theories that differ at those very high scales is very large and not very constrained by any observation we can think about.
That's definitely true, Doctor. Thank you. We have another question. This is, aren't the broken symmetries telling us that, in fact, conservation is not a universal truth? Is it possible to have conservation of quantities only for a particular kind of system, but not in the whole universe as a set?
Yes. So the conservation of, in physics theories, as I said, the mathematics predict certain conservation laws. If you go to a different mathematics, you'll have different conservation laws, perhaps. Or some of them, as I said, we started with C, P, and T as separate symmetries. Now we know, okay, each of them individually is broken, but the product CPT is true in the standard model. When you go beyond the standard model, maybe the product CPT isn't a symmetry. Then you have to be writing theories which are not field theories. You have to go to a new mathematics to find some theory that breaks that symmetry. So that's possible. We don't know the answer, and we should be exploring it. And we should also be looking for how could we test if we were to find an experiment that violated CPT, that would challenge theorists, because most of the theories we write as field theories, not string theories, but field theories, have CPT as a symmetry. We would be forced into some new domain of theory, as we were when we found CP violation and nobody could write a theory that had CP violation. We were forced into theories with more particle types. So, you know, sometimes the experiment comes first and forces the theorists to rethink. Sometimes the theory comes first and predicts something that experimentalists find afterwards. But both ways are important.
Thank you. I think we have time for one last question, and this is, what do you think of the alternatives to the axions? There are some alternatives in string theory that have been recently kind of ruled out by the LHC results, for example. So what would be the future for?
I'm not quite clear which way this is going. I mean, first of all, for a long time, people were searching for what are called WIMPs, weakly interacting massive particles, as dark matter candidates, which are consequences of supersymmetry. And it's not that supersymmetry is ruled out, but the range of parameters, which was called the WIMP miracle, is ruled out. And so the attractiveness of that particular option to physicists in general has gone down, and the attractiveness of axions for no good reason went up, because they're the only other consequence lying around. I mean, there was no good reason the axion was ignored while everybody was searching for WIMPs, and there's no good reason that the WIMPs are ignored, because they don't have to be the answer to it. This is the problem. You can write lots of theories to explain dark matter. You can add some kind of particle to your theory and explain dark matter. It's just not very attractive to do because there's no clues as to what it should be. So we're much more interested in the candidates that come from something else. In our case, from trying to explain the strong CP problem. In the case of the WIMP, from supersymmetry and the hierarchy problem explained. So a candidate for dark matter that also relates to the explanation of another problem is much more attractive than a candidate for dark matter that we just add some light weakly interacting scalar particle to our theory, or some heavy weakly interacting scalar particle to our theory for no good reason, and say that's dark matter. But it could be that the world isn't kind to us and dark matter is something that's completely unrelated to any other interesting problem. So we don't know.
I hope that some future experiments can shed light on this subject. But thank you very much, Doctor. It has been a pleasure having you here with us. And I
You're
remind
very welcome.
audience that in a few minutes we're having a discussion panel with Dr.
Okay. And so we go out of this one and into the other one, huh?
Yes, in a few minutes, sure.
Okay. Well then, I will say goodbye for now, and I will reappear in the other panel.
Sure.